Hello, we are once again on PSI Physics. In our last lesson, we dealt with relative velocities. We came out with a definition for relative velocity, which we can apply in all cases. We came out with the fact that given the relative velocities VA and VB of two bodies, the velocity of A relative to B is given by VAB equals VA minus VB. We now come to a case in which we are rowing or paddling a canoe or boat in a few different situations. For example, when the ferryman attempts to row with a current against a current that is in the same direction or against the direction in which the river or stream is moving. In a case in which he attempts to cross the river at right angles or any other angle to the banks of the river. It will interest you to know that the situation of our ferryman, the one who is rowing the boat, is similar to that of a pilot who pilots an airplane under different wind direction. It means that the movement of water, represented by W in the case of the ferryman, can be compared to the movement of wind, W, in the case of the pilot. Since the ferryman or the canoe or boat is being observed from the banks of the river compared to a bus stop, and the aeroplane is observed from the ground or airport, the banks B of the river is comparable to the airport. The canoe C is comparable to the aeroplane A. Let us now examine the case of the ferryman. By the end of this lesson, you should be able to 1. Apply your knowledge of relative velocities to the situation faced by a ferryman or a pilot as they move a canoe or aeroplane through water or the wind. 2. Distinguish between cause vector, water, wind vector, and track. 3. Handle problems involving a ferryman rowing a boat when a river is in motion. Well, let's now consider a stream 10 meters wide, flowing from west to east, and a man who can row a boat in still water at 4 meters per second. This means that the magnitude of the velocity of the canoe relative to water, VCW, is 4 meters per second. Let the magnitude of the velocity of the water relative to the banks B be 3 meters per second. That is VWB equals 3 meters per second. The velocity of the canoe C relative to the banks is given by VCB equals VCW plus VWB. That is vector sum. Let's call this equation 1. Note how the relative velocity has been obtained. On the right-hand side, VCB starts with C and ends with W. And so the second term, VWB, starts with W and ends with B. Thus, for the right-hand side, we start with C and end with B. Look at the left-hand side, which must equal the right-hand side. It also starts with C and ends with B. Look at it again on your screen. Now, for the purposes of notation and naming, VCW equals cos vector, VWB equals water or wind vector. That is wind vector when we are dealing with the flight of an aeroplane. And VCB equals track. Thus, equation 1 can be read as track equals cos vector plus water vector. Let's now consider the situation in which the ferryman rows the canoe with the current. That is, canoe is moving in the direction of motion of water or current. VCB equals VCW plus VWB becomes VCB equals 4 plus 3. This gives us 7 meters per second. On the other hand, if the man rows a canoe against the current, we have VCB equals VCW plus VWB, becoming VCB equals 4 plus minus 3. This gives us 1 meter per second. Taking the direction of motion of the canoe as positive, that of motion of the water becomes negative, hence the negative 3. Again, if the ferryman rows the canoe or boat at right angles to the banks with the water moving in the west-east direction, the situation is as shown on your screen. Look at the smaller triangle, triangle OAD. Which gives an important information. The track is a path actually taken by the canoe or airplane and is the resultant vector, and as usual is represented by double arrows. The course represents the direction in which the canoe is headed. Let's answer another question. If the ferryman heads the boat at right angles to the banks, determine the relative velocity with which he crosses the stream or river. Relative velocity with which he crosses the river, VCB, equals track into bracket, that is from the diagram, VCB squared equals VCW squared plus VWB squared. This gives us 4 squared plus 3 squared equals 25. The square root of this gives us 5 meters per second, which equals the speed with which he crosses the river. For the direction, tan theta equals 3 divided by 4. This equals 0.75. Finding the tan inverse of this gives us 36.9 degrees. It implies that he crosses with a velocity of 5 meters per second in the direction 36.9 degrees. Let's try another question. Assuming he heads the boat at right angles to the banks, how far downstream will he land the boat? Diagram shows triangle OAD and triangle OBC, which are the corresponding triangles, because their corresponding angles are. The corresponding sides of triangle OAD and triangle OBC are proportional, implying OB divided by OA equals BC divided by AD. This equals OC divided by OD. This implies 10 divided by 4 equals BC divided by 3. This equals OC divided by 5. Let's call this equation I. The required distance equals BC. This equals 10 times 3 divided by 4. This equals 7.5 meters. Thus, he lands the boat 7.5 meters downstream. Let's pick another question. What distance does the ferryman travel before landing at the opposite bank? Here, the distance required equals OC. From diagram, OB divided by OA equals OC divided by OD. This equals 10 divided by 4 equals OC divided by 5. This implies OC equals 10 times 5 divided by 4 equals 12.5 meters. Alternatively, we can apply the Pythagoras theorem to the triangle OBC as follows. OC squared equals OB squared plus BC squared. This equals 10 squared plus 7.5 squared. This gives us 100 plus 56.25, implying OC equals 12.5 meters. The ferryman travels a distance of 12.5 meters to land the canoe at the opposite bank at sea. Let's consider this question again. How long does the boat travel to land at the opposite bank when it is headed at right angles to the banks? Distances traveled, OC equals 12.5 meters. Speed at which he travels equals VCB equals 5 meters per second. It implies time travel T equals distance divided by speed. This equals 12.5 divided by 5, which equals 2.5 seconds. This gives us the time of travel along the track. Assuming the stream was still, how long would it take the ferryman to cross when the boat is headed at right angles to the banks? In this case, boat is headed along OA and lands at B, traveling a distance of 10 meters. That is, distance traveled equals 10 meters. Speed of travel equals 4 meters per second. Implies time of travel equals distance divided by speed. This equals 10 divided by 4, and it gives us 2.5 seconds, which equals time of travel along the course. Therefore, it implies time of travel along the course equals time of travel along the track. If the ferryman wants to move in a direction perpendicular to the banks, that is, land at B directly opposite his starting point, when the river is moving, in what direction must he head the boat, and with what speed does the boat move relative to the banks? In this case, it means he must head the boat so that the boat will move at right angles to the banks. That is, the track will be OB and the water vector is still west-east. Thus, boat must be headed along OF, that is the course vector OF, as shown on the screen, so as to achieve the required track OB. Thus, in the diagram, we have VWB equals water vector, VCW equals course vector, and VCB equals track. It implies boat is headed along OF, where sine theta equals 3 divided by 4 equals 0.75. This implies theta equals 48.6 degrees. The boat must be headed in a direction north 48.6 degrees west, or on a bearing of 311.4 degrees. That is 360 minus 48.6 equals 311.4. Speed with which the boat crosses the river equals VCB. Thus, from the diagram, VCB squared equals 4 squared minus 3 squared. This gives us 7, and the square root of this gives VCB equals 2.6 meters per second. Thus, the boat is headed in the direction 311.4 degrees and crosses with a speed of 2.6 meters per second. Well, I hope this has been interesting. Assuming you were swimming, can you put yourself in the shoes of the ferryman as you swim with and against the current? If you were to swim, attempting to cross the river, heading yourself at right angles to the banks, can you now imagine where you will land? If you want to land directly opposite your starting point, I hope you know how to take into consideration the direction in which the water is moving in order to determine how to move, in order to see yourself moving at right angles to the banks and land exactly at the opposite bank. Well, in this lesson, the concept of relative motion have been used to handle the problem of the ferryman, and by extension, the problem of the pilot, in which the ferryman heads a boat at right angles to the banks, but lands downstream because the stream is moving. We also considered a situation in which the ferryman chooses the direction perpendicular to the banks of the river as his track and chooses a course or direction to head the boat in order to achieve this track. Well, can we end the lesson by taking a problem home to test our understanding of what we have done today? Question. Define the term relative velocity. B. A man rows a boat in still water at 6.0 kilometers per hour. He wishes to row due north across a river 3.0 kilometers wide, which is flowing due east at 2.0 kilometers per hour. Calculate I, the direction in which he must head the boat. II, the time taken to reach the other bank. The answers to the B part of the question are I. Theta equals 19.5 degrees, meaning the boat will be headed in the direction north 19.5 degrees of west, or on the bearing of 340.5 degrees. 2. The speed with which he crosses the river would be equal to 5.66 kilometers per hour, and the time of travel would be 32 minutes. Well, this is where we end today's lesson. I hope you've enjoyed it. Till we meet for the next lesson. Goodbye.